Morning. Myself, Radha Ragini. Today we are going to talk about the principles of green chemistry. Actually, there are 12 principles of green chemistry. Before getting into the topic, let's have a brief discussion of what is green chemistry and what are its uses and all. Actually, the green chemistry is the design of chemical products and processes that reduce or eliminate the use of or generation of hazardous substances. Green chemistry applies across the life cycle of the chemical products, including its design, manufacture, use, and ultimate disposal. Hence, the green chemistry is also known as a sustainable chemistry. And it is very important to learn about the principles of green chemistry. These are the 12 principles of green chemistry, of which prevention, atom economy, less hazardous chemical synthesis, designing safer chemicals, safer solvents and auxiliaries, designed for energy efficiency, use of renewable feedstocks, reduced derivatives, catalysis, design for degradation, real-time analysis for pollution prevention, and inherently safe chemistry for accident prevention. All these 12 principles must be kept in mind while synthesizing any product, and it is of utmost importance to know about these principles of green chemistry. The first principle is a prevention. It is better to prevent waste than to treat or clean up waste after it is formed. A very famous idiom is there where the prevention is better than cure. So instead of treating the waste that is obtained from the industries, instead of treating these industrial effluents, if this industrial effluent production is reduced, or any less poisonous industrial effluents or less harmful industrial effluents are produced, then the environment and human health will not be affected. Such synthetic processes must be adopted. Let me give you some case studies where these industrial effluents have shown a profound effect on the health of the citizens. In Niagara, a canal was there, that is a Love Canal, where the chemicals and plastic companies have used uh, it as a bed for dumping the chemicals. That is, in 1930 to 1950, they have used this canal for dumping the industrial effluents. The land was then used for new school and housing track at that time. The chemicals leaked through the clay cap that sealed the dump. It was contaminated with at least 82 chemicals, of which very poisonous chemicals are present. Some poisonous chemicals like benzene, dioxins, chlorinated hydrocarbons, all these chemicals were present in that dump, and all this because of the leakage of that cap. All these chemicals have mixed with the clay, and they have contaminated the whole land with all these poisonous chemicals. Hence, the health has affected the citizens living in that area. The effect was to such a high extent that the nervous system that it has affected the nervous system of the children. Even the birth defects were also increase, means the newborn babies suffered with several syndromes, some nervous problems. All these were faced by the people living in that area only because of the industrial effluents that were dumped in the canal. Another very good example for this is the Cuyahoga River in Ohio. There were many things being dumped in this river, Cuyahoga River, like gasoline, oil, paint, metals, and so many were dumped. The river became so famous, and it was called as a rainbow of many different colors because of these chemicals. Some chemical because of the chemical reactions that were taken place inside this water and all. Several colors were displayed on the surface of the river, and it got that name. Even the Times magazine has published an article where saying that some river, chocolate brown, oily, bubbling with subsurface gases, it oozes rather than flows. Actually, the river is supposed to flow with water, but this river, it was oozing the chemicals as if it is synthesizing the chemicals, and it is oozing out. So when the and criticism was also written saying that if anyone falls into that river, the person will not drown. Actually, the persons, if they fall into the river and if they don't know swimming and all, they will drown into the river. But if anyone by accidentally falls into the river, they will decay. They won't drown, but their body will decay. See the extent of um, the harmness or harmful effects that were caused because of this dumping. Even actually it has captured the fire in the river because of all these industrial effluents that were dumped in the water. The second principle is the atom economy. The synthetic methods should be designed to maximize the incorporation of all the materials used in the process into the final product. The selection of the synthetic methods is very important. Actually, the percentage of yield can be calculated by actual yield by theoretical yield into 100. While selecting the synthetic process, several questions have to be kept in mind, and acceptable answers must be able to be answered to these questions. Some of these questions that have to be posed by the posed by the person who is synthesizing the chemical products are what co-products are made in this synthetic process. If I synthesize a particular compound, what co-products are obtained, how much waste is generated during the synthetic process, is the waste benign waste, are the co-products benign or usable? How much energy is required? Are purification steps needed? How solvents are used? Is a catalyst truly a catalyst? All these questions must be posed by themselves so that they go for the correct synthetic process. Just a second. Now, atom economy. This can be calculated by using the formula of the total number of atoms utilized by the reactant by the same of reactants into 100. Several the importance must be given to the stoichiometric control. How efficient is the reaction in practice? What kind of solvents are used? Are these solvents are efficient so that there does not cause any harm to the recipients that use those products and all? How much amount of energy is utilized? All these points must be kept in mind, and then synthetic process must be selected. The third principle is less hazardous chemical synthesis. Okay, whenever practicable, synthetic methodologies should be designed to use and generate substances that possess little or no toxicity to human health and environment. See, the synthetic process really plays very important role. The synthetic methodologies must be designed in such a way that their final product should not cause any harm to the environment and even to the humans. For example, let us take up the example of synthesis of polycarbonate by phosgene process. Actually, this is a synthetic reaction that is followed for the synthesis of polycarbonate. But the disadvantages of using CH2Cl2, here CH2Cl2 is used as one of the reactant for the synthesis of polycarbonate. But there are several disadvantages, like phosgene is highly toxic and corrosive. It requires large amount of CH2Cl2 methylene dichloride, and polycarbonate contaminated with chlorocompounds. If chlorocompounds are present, then it will definitely have something or the other effect on the users. So the final product that is obtained, that is nothing but the polycarbonate, has got some chlorine impurities which will affect the users because phosgene is used as one of the reactant. So another that is one synthetic procedure. As that synthetic procedure is not that efficient, the polycarbonate can also be synthesized by solid state process. This is the reactions, and these are the reactants that are used in the synthesis of polycarbonate. The advantages of this method is diphenyl carbonate synthesized without phosgene. Nothing but polycarbonate is synthesized without using of phosgene, eliminates the use of CH2Cl2, and high quality polycarbonates, that is the final product is of high quality, no chlorine impurities will be present. So we have to select those synthetic processes which will not affect the health of humans and even should not affect the environment. The fourth principle is designing safer chemicals. The chemical products should be designed to preserve efficacy of the function while reducing the toxicity. Actually, in ships, the hull of the ship is usually coated with the anti-fouling agents, so that the corrosion can be prevented. Actually, this is a case study where that anti-fouling agent has affected the marine and the what water of that sea. Actually, anti-foulant agents are generally dispersed in the paint as it is applied to the hull, as I told earlier. Organotin compounds have traditionally been used, particularly tributylene oxide is used. This tributylene, sorry, Tributyl tin oxide works by gradually leaching from the hull, killing the fouling organisms in the surrounding area. Because of this action of tributyl tin oxide, it is getting mixed with the water that is present around this hull, and the organisms or the marine animals that were living in that water have were incorporated with this chemical, and they have entered the food chain. For example, let us take fish. The fish has grown in the water that has tributyl tin oxide. The fish now, in the body of the fish has some traces of tributyltin oxide. The humans like us would like to eat the fish, and we have by mistake we have eaten that fish. Our body also will get the traces of tributyltin oxide, which are very toxic to humans. Not only to humans, even for that fish or the for that marine animals also, that toxin is very dangerous. So, the such compounds should not be used, which will affect the marine or the humans that have come across through this chemical. Other alternative methods must be adopted. Organotin compounds are chronically toxic to marine life and can enter food chain. They are bioaccumulative. And the active ingredients of C9211. This C9211 can be used as a substituent for that chemical. Actually, the C9211, the chemical ingredient is 4,5-dichloro 2N-octyl 4-isothiazolene 3-on. It is in shortcut, it is called DCOI. It is a member of isothiazole family of antifoulants. If this chemical is used, this will not affect the water that it has come in contact with. Actually, the working of this chemical is a bit different. This works by maintaining a hostile growing environment for marine organisms. When organisms attach to the hull, if the organisms attach to the hull, then only that organism will be affected. Unlike the previous chemical, when organism gets attached to the hull, the proteins at that point of attachment with the hull react with this DCOI. This reaction with the DCOI prevents the use of these proteins for another metabolic processes. The organisms that detaches itself and searches for more hospitable surface on which it grows. Only organisms attached to the hull of the ship are exposed to the toxic levels of the DCOI, but not the other animals which are living in that water. Readily biodegrades once leached from the ship. That is, the half life is less than 1 hour. If at all this DCOI get mixed, if at all it get mixed with water, as its half life is very less, that is of a 1 hour, this toxic effect will disappear after 1 hour. So these kind of chemicals must be selected for use and applications. The fifth principle is the safer solvents and auxiliaries. The use of auxiliary substances means the solvents, separating agents, and some which are very much required for during the synthetic process should be made unnecessary whenever possible, and when they are used, they must be innocuous. Safer, so as I told earlier, the only safer solvents must be used. The solvent, if the solvent is not safe, then that solvent must be substituted. Water, it's a very good solvent and it is a safer solvent. As much as possible, water must be used as a solvent so that it does not affect the consumers of the chemical products. Now, new solvents like ionic liquids, supercritical fluids, they will also have a very less effect or no effect on the health of humans or even on the environment. So, such solvents must be used. Actually, there are several solvents which I have given few examples. The solvents which can be preferred are water, acetone, ethanol, 2-propanol, 1-propanol, ethyl acetate, isopropyl acetate, methanol, methyl ethyl ketone, methyl ethyl ketone, 1-butanol, and tertiary butanol. These are some of the chemicals which are preferred which are preferred to be used as a solvents during the synthetic process. From this, the second category are the usable solvents. If these solvents are not suitable for the synthetic process, then these solvents can be selected. Now, some of them are cyclohexane, heptane, toluene, methyl cyclohexane, methyl tertiary butyl ether, isooctane, acetonitrile, 2-methyl tetrahydrofuran, tetrahydrofuran, xylenes, dimethyl sulfoxide, acetic acid, ethylene glycol. These are some of the chemicals which are usable, not preferred, but they can be used. Means up to certain extent they can be used. But the undesirable solvents that should be avoided are pentane, hexanes. Means a heptane can be replaced with hexane actually. Hexanes, diisopropyl ether, diethyl ether, dichloromethane, dichloroethane. All these chloro compounds should not be used actually. Chloroform, dimethyl formamide, and methyl polypyrrolidanone, pyridine, dimethyl acetate, dioxane, dimethoxyethane, benzene, carbon tetrachloride. These are some of the chemicals which should not be used and must be avoided as a solvents during synthetic process. Coming to their flash points, actually the flash points must be see, for pentane, the flash point is minus 49 degrees centigrade, which is very low flash point and good alternative available. So, these flash points must be as low as possible. Then the solvent can be considered as a preferred solvent. Hexane, it has a flash point of minus 23 degrees centigrade, and the reason is the reason that hexanes can be preferred is they are more toxic than the alternative heptane classified as HAP in the US. Coming to the diisopropyl ether, its flash point is minus 12 degrees centigrade. It is a very powerful peroxide former, good alternative ethers available. Next is the diethyl ether. It has a flash point of minus 40 degrees centigrade. Very low flash point, good alternative ethers are available. Dichloromethane. Okay, actually its flash point is not available. High volume use regulated by EU Solvent Directive, classified as HAP in the US. Next comes dichloroethane, which has a flash point of 15 degrees. It is carcinogenic and it is classified as HAP in the US. See, the flash point is really high, 15. Chloroform, and it should not be used because it is a carcinogen and it is classified as HAP in the US. Dimethyl formamide, it has very high flash point of 57 degrees, highly toxic, strongly regulated by US solvent directive, and it is classified as HAP in the US. And methyl polypyrrolidinone, and it has a flash point of 86 degrees peak, and it is toxic, strongly regulated by EU solvent directive. Next comes the pyridine. It has a flash point of 20 degrees and carcinogenic and mutagenic, reprotoxic. That is, these are called the CMR the third category carcinogens, and they are highly toxic. They have a very low threshold limit for worker exposures. Workers should not be exposed to pyridine for the longer time. Next comes dimethyl acetate. It has a flash point of 70 degrees. It is highly toxic, strongly regulated by EU solvent directive. Next comes a dioxane. It has a flash point of 12 degrees. It is a CMR category with class 3 carcinogens, classified as HAP in US. Dimethoxyethane, it has a flash point of 0 degrees and CMR category 2 carcinogens, and it is highly toxic. It should not be used actually. Next comes a benzene. It has a flash point of minus 11 degrees. Better to avoid the use of benzene. Okay, it is strongly regulated in US and EU. Next comes carbon tetrachloride. The use of carbon tetrachloride must also be avoided because it comes under the third class carcinogen, and it is toxic, ozone depleter, banned under the Montreal Protocol, not available for large scale up. At laboratory scale, carbon tetrachloride can be used, but large scale carbon tetrachloride should not be used because it depletes the ozone layer also. Strongly regulated in EU and ES. This is about the details of why these solvents should be avoided. Now this is a solvent replacement table where the undesirable solvent can be replaced with another solvent. For example, in a synthetic process, if pentane is used, instead of pentane, heptane can be used. Similarly, hexanes can be replaced with heptanes. Diisopropyl ether or diethyl ether can be replaced with 2-methyl tetrahydrofuran or tetrabutyl methyl ether. Similarly, dioxane or dimethoxyethane can be replaced with 2-methyl tetrahydrofuran or tertiary butyl methyl ether. Now, the chloroform, dichloroethane, or carbon tetrachloride can be replaced with dichloromethane. Dimethyl formamide, dimethyl acetamide, or N-methyl polypyrrolidinone can be replaced with acetonitrile, and pyridine can be replaced with a triethyl nitrogen. Dichloromethane can, if dichloromethane is used in the extraction process, then ethyl acetate can be used, and even toluene also can be used, and these are different chemicals which can replace dichloromethane. Similarly, if dichloromethane is used in chromatography, in chromatographic methods, then it can be replaced with heptane or ethyl acetate, and then benzene can be replaced with toluene. These are some of the alternative agents where the undesirable solvents can be replaced. As per the Pfizer's rule, the use of solvent replacement guide resulted in 50% reduction in chlorinated solvent use across the world of their research divisions. More than 1600 lab-based synthetic organic chemists and 4 scale-up facilities during 2004 to 2006. Reduction in the use of an undesirable ether by 97% over the same 2 years period. The reduction has reduced to 97% C because of the replacement of undesired chemicals. The heptane used over hexane and pentane, because the hexane it is more toxic in nature, um, and so it must be replaced, and so they are replaced with heptane. Even the supercritical fluids, these fluids also can be are very less toxic and also can be used as a solvent replacements where the solvents used are toxic. The sixth principle is the design for energy efficiency. The energy requirements should be recognized for their environment and economic impacts and should be minimized. Synthetic methods should be conducted at ambient temperatures and pressures, because at very high temperatures and very high pressures there is possibility that the accidents may take place during the synthetic methods. Mm. Now, the energy is while synthesizing a chemical product or any product, the energy in different forms is consumed, like thermal. For thermal reactions, some amount of energy used for cooling, for distillation, for equipment, for photo and microwave. Or in all these, the energy is consumed, and the source for this energy is obviously either the solid fuels, liquid fuels, or gaseous fuels like coal, oil, and natural gas. So, the energy coming to this energy usage, the chemicals and petroleum industries account for 50% of the industrial energy usage. Almost quarter of the energy used is consumed in distillation and drying processes. Alternative energy sources must be used where which are renewable, like renewable energy sources must be used instead of non-renewable energy sources. Two examples are two commercial photochemical processes are caprolactam process and vitamin D3 process, and vitamin D3. These are the chemical reactions that are involved in this process. Mm. The wavelengths between 1 millimeter and 1 meter, fixed frequency of 2.45 gigahertz, more directed source of energy, heating. These are the advantages because of the alternative energy sources. Okay, heating rate is 10 degrees centigrade per second is achievable. Possibility of overheating, solvent free conditions are possible. Interaction with matter characterized by penetration depth. Okay, next, the seventh principle is the use of renewable feedstocks. A raw material or feedstock should be renewable rather than depleting whenever technically and economically practical. So what is supposed to say is the raw material must be renewable. Petroleum products, this is an example where indicating that renewable raw materials must be used. Sorry. Okay, now let us take up the example. The fermentation of glucose in presence of bacteria and propanoic acid can be performed, and similar to polypropene and polyethylene. These reactions are similar to polypropene and polyethylene, and these are biodegradable. So, by these kind of renewable sources must be used for the synthetic processes. See here also the polymers, they are synthesized from the renewable sources, because as these polymers are synthesized from the renewable sources, they will show very less effect on the environment. Similarly, levolinic acid, this levolinic acid can be synthesized from the paper mill sludge, which is renewable. Some agricultural residues, the waste wood, and also the municipal solid waste and waste papers. By using all these renewable sources, a levolinic acid can be synthesized. The scientist was also awarded who the scientist who discovered this process was also awarded with the Green Chemistry Challenge Award in 1999, and he was well recognized and became very famous because of the of uh, discovering this synthetic process. These are the examples where the levulinic acid as a platform chemical, all these can be synthesized. The next principle is reduce derivatives. Unnecessary derivatives should be avoided whenever possible. Here, unnecessary derivatives means blocking groups, physical and chemical processes, the temporary or modification of the physical and chemical processes, deprotection groups, protection groups. All these must be, all these are unnecessary and they should be avoided whenever possible. The protecting groups, the two synthetic steps are added each time one is used. Overall yield and atom economy will be reduced. Protecting groups are used because there is no direct way to solve the problem without them. The ninth principle is a catalysis. The catalytic reactants are superior to stoichiometric agents. The catalytic reactants are very selective and they play very important role in, in increasing the rate of the reaction. The kinetics will be very much affected because of these catalysts. Actually, the catalysts are used in homogeneous and heterogeneous reactions. When we consider the properties of the when we compare the properties of heterogeneous and homogeneous reactions, we majorly find these differences. Excuse me. We majorly find these differences distinct solid phase, and coming to the homogeneous, they will be present in the same phase as reaction medium. For example, in heterogeneous, the reactant and or the catalyst will be in different phase. One will be in solid, one will be in liquid. But coming to the homogeneous, both must be in the solid phase. Next comes a ready. These can be readily separated. They are difficult to separate. These are readily regenerated and excuse me. These are readily regenerated and recycled. These are expensive or difficult to recycle. These here the rates are not fast, but these have a very high rates. Diffusion is limited, not diffusion control. It means diffusion cannot be controlled. Sensitive to poisons, and these are robust to poisons. Low selectivity, and these are high selectivity. Long service life, short service life, and similarly high energy process, and this is a mild conditions. Very mild conditions must be maintained in the homogeneous reactions. Poor mechanistic understanding, and the mechanism is well understood for the homogeneous reactions. So when we observe these properties or the points that are included in the homogeneous and heterogeneous reactions, some are very useful in heterogeneous, and some properties are useful in homogeneous. The properties are highlighted here readily. These can in heterogeneous, the advantages are this can be readily separated, readily rearranged and recycled, and they have a very long life. The long service life is present. Coming to the homogeneous, they have very high rates, they are robust to poisons, they have high selectivity, and mild conditions can be must be maintained for homogeneous. These are the advantages, but if all these are present in one, then it is proved to be the best. So, by using green catalysts, these all advantages can be brought together. So, catalysts plays an important role in green chemistry. See, this is an example of the biocatalyst. The biocatalyst can be obtained from, these are nothing but, sorry, they are nothing but the enzymes or the whole cell microorganisms. Because of the use of the biocatalyst, we get many benefits like fast reactions due to correct orientations. The orientation of site gives high stereo specificity, the substrate specificity, water soluble, naturally occurring, moderate conditions, possibility for tandem reactions. All these are the advantages of using the biocatalysts. Next principle is a design for degradation. Chemical products should be designed so that at the end of their function, they do not persist in environment and instead break down into innocuous degradation products. Persistence, for example, let us take up the example sulfonated detergents. About these, that these are the alkyl benzene sulfonates. They form in sewage water, sewage plants, rivers and streams. They are persistent. Their persistence is very high due to long alkyl chains. Introduction to alkene group in the chain increased degradation. So sulfonated detergents are not preferred. Now similarly, the chlorofluorocarbons, these do not break down and they persist in atmosphere and contribute for the destruction of the ozone layer. DDT, the bioaccumulation of the DDT will cause thinning of the eggshells. So the byproducts or the what to say the products or the byproducts should have very less persistence, even if they are persistent in the environment, that can be either in the air, water or anywhere. Their persistence must be very less. See, degradation of the polymers. Let us take up the example of polylactic acid. This polylactic acid is manufactured from the renewable sources. Means the corn, wheat, as I said in the previous slide, corn or wheat and agricultural waste in future, the polylactic acid can be used. Okay, uses only 20 to 50% fossil fuels than conventional plastics. Now, polylactic acid products can be recycled or composted. So these kind of products must be encouraged. Now, the 11th principle is real time analysis for pollution prevention. Analytical methodology is needed to be further developed to allow for real time in process monitoring and control prior to the formation of hazardous substances. The real time analysis for a chemist is the process of checking the progress of the chemical reaction as it happens. Knowing when your product is done can save a lot of waste time and energy. For analyzing a reaction, what do you need to know? How do you get this information and how long does it take to get it must be answered. These if these answers the answers for these questions are satisfactory, then you can go for that chemical reaction. The last principle is inherently safer chemistry for accident prevention. Substances that form a substance used in chemical process should be chosen so as to minimize the potential for chemical accidents, including their release, explosions and fires. The best example for this is a Bhopal gas tragedy, which is really has made a historic event for several centuries. Also, for upcoming centuries, also this Bhopal tragedy must will be remembered, because actually, in this is the worst industrial accident in history. What happened is 40 tons of methyl isocyanate were accidentally released when a holding tank overheated at a Union Carbide pesticide plant located in the heart of the city of Bhopal. 15,000 people died and hundreds of thousands were injured. Because of this gas, the future generations also got affected. See, this has really uh, made a historic event. The chemists have tried to avoid the things by explode, light on fire, or age sensitive. All these must be studied while during the synthetic process itself. These must be studied. In real world, when these things happen, lives are really lost. Actually, this Bhopal gas tragedy has happened in India on December 3rd in 1984. This cyanide gas leaked from the Union Carbide factory, killing thousands instantly and injured many more. Up to 20,000 people have died as a result of exposure. More than 1,20,000 still suffer from ailments caused by the exposure. Actually, what happened is methyl isocyanate used to make pesticides was being stored in large quantities on site at that place. This methyl isocyanate is highly active and it is an exothermic molecule. Most safety systems either failed or were inoperative. Okay, actually the The steel tank which is used to store this methyl isocyanate got corroded, and because of the corrosion product, this the reaction has the rate of the reaction also has increased a lot, which has affected very in a toxic level. The water was released in the tank holding this methyl isocyanate. The reaction occurred and the methyl isocyanate rapidly boiled, producing large quantities of toxic gas. Next, the chemical industry accidents. The U.S. Public Interest Research Group reported that the chemical industry had more than 25,000 chemical accidents since 1990 in US. More than 1,800 accidents a year, or 5 a day. And for per day, 5 chemical accidents were taking place in US. And top three are the BP, Dow, and DuPont, where one third of the accidents were recorded. Okay, here by now all the principles of the green chemistry were completed. Thank you.